Okay, so let's pick up where we left off. We were just talking about converting square units or units to a higher power, and we had just a quick example of how that works. So you want to be on the lookout for that. We do very regularly encounter squared units, like acceleration is in meters per second squared. So it's a skill that we need to have. So let's talk about this example 3. This is a little bit different. So it says the body mass index takes into account your mass in kilograms and your height in meters. The problem with this is that in some countries like ours, we like to use pounds, which is not a unit of mass, it's a unit of weight, and we like to use inches or feet for our measurement of lengths. So if we're hoping to use this formula, then we need to be able to alter the formula in a way that will allow us to enter our quantities in the desired units and still get the correct BMI. If we were to just use the formula and enter it with the wrong units, then our BMI would be calculated improperly. So the first thing we need to do is we need to look at how to convert between the units that we're measuring in, pounds to kilograms, or inches and meters. Now, the one really important distinction here is what they've said here. Pounds is a weight. So we're doing something more than unit conversion here, and we have to just be really careful of that. And it's a problem with convention. In our country, we like to measure the mass in pounds, which is a weight unit. It's a force of attraction. And the problem with doing that is that your weight depends on the Earth, and it depends on how close to the Earth you are. So your weight changes when you go up into the International Space Station, or when you're on the moon, your weight changes, but your mass does not. Your mass is invariant. The amount of matter that you're made up of is always the same. So pounds is not a very good unit of measurement because we're indirectly trying to talk about mass, but we're doing it with a unit and a quantity that can change based on where we are. So not very good, but it's the adopted convention, so we have to deal with it. Anyway, all right, so let's try to convert from pounds to kilograms. So what we want is we want a mass in kilograms, and we're going to enter our mass in pounds, or our weight, sorry, in pounds, and we need to convert it into kilograms so that it works with the equation for BMI. So we need a conversion between kilograms and pounds. And if we go to the conversion factors, we can see, let's see here. Now you can see this is in parentheses again because weight is not a unit of mass, so we just really want to keep that straight. Anyway, 1 kilogram has a weight on Earth of 2.205 pounds, where we have our standard acceleration of gravity on the surface of the Earth. So lots of fine print there, but that's what we've got. So we're going to put that in for our example. So 1 kilogram for every 2.205 pounds. That's going to be one conversion. So if we were to enter our mass in pounds, then we can convert it into the correct unit that way. All right, we need to do this again for height. So we need our height in meters, but we're going to be providing it in inches. So we need a conversion that will give us meters and inches. And if we go back to our conversion chart here, let's see if we've got something. Now, in this case, we don't have a conversion between meters and inches. We have a conversion between meters and feet. So we're going to have to deal with that. So we're going to have meters to feet, and then the conversion from feet to inches won't be so bad. Let's see here. So we'll have feet up here, inches down here, and every 1 foot has 12 inches. We can see that inches is going to cancel out with that inches. The feet dividing by feet. There we go. So we need meters to feet, and that's going to be 0.3048. Okay. So now what we're going to do is we're going to alter the formula for the BMI. Try to do this in a different color, I guess. So the BMI is your mass in kilograms over your height in meters squared. So what we're going to do is we know that we're going to be entering our mass in pounds, and we need to convert. So instead of mass in kilograms, we're going to have our mass in pounds times 1 over 2.205 pounds kilograms. And then down here we need our height in meters. We're going to enter instead our height in inches and multiply by this conversion, which was 0.3048 over 12. And that's going to be inches and meters. Now that needed to be squared, so we're going to take this whole thing and square it. So now we should be able to enter our weight in pounds and our height in inches and get the correct BMI with our new conversion factor. If we simplify this, let's do that real quick. So we're going to have 1 divided by 2.205 divided by the quantity 0.3048 divided by 12. And that was all squared. And that gives us our conversion factor, which is, let's go out to 2 decimal places. So we'll have 702.95. And our units in this case, if we're looking at what's going on here, we're going to have kilograms, inches squared, and then meters and meters squared and pounds. So this inches is on the bottom fraction of this complex fraction. It's going to flip up to the top. So we're going to have kilograms, inches squared over pounds, meters squared. This is our conversion factor, and so we can enter our mass in pounds and our height in inches and still get the correct BMI. All right. Sometimes for dimensional analysis, we like to do a unit analysis where we just write the units to verify that an equation is at least yielding the correct units. So let's look at what's going on here. Velocity has the units of meters per second. Meters is a unit of length, and seconds is a unit of time. So these square bracket blocks here are telling us a dimension of length, a dimension of time. And obviously time would be measured as a dimension of time squared. So when we cancel out one dimension of time with one dimension of time, we get a length times a time. And we can see in this case that the units yielded from this equation do not match the units we started with, because position is measured in length, which or with the units meters, which is the dimension of length. So since they don't match, this is not an appropriate equation, and we know that we've made a mistake somewhere in deriving this equation. Since we had too much units of time, we could say, well, maybe it should just be velocity times time, and then here it cancels out, and we get the same unit, dimensional unit on both sides. So this is a way to make sure that a formula that you derive is correct. And this is a very powerful tool for checking yourself during the exam if you need to derive a formula that's specific to that problem. You can really catch a lot of mistakes this way without doing something that would take more time. All right, what I'd like for you guys to do now is we're going to do some check your understanding questions. So I want you to look at the following questions and pause the video and try to answer them, and then when you're done, unpause the video and we'll go over them. Okay. So the first one says, is it possible for two quantities to have the same dimension but different units? And this is, in fact, possible. I could have the dimension of length, but I could measure it in meters, or I could measure it in inches. So that's fine. The next question, is it possible for two quantities to have the same units but different dimensions? So they're asking, could I say maybe have seconds as a unit and seconds as a unit, but one of them is a measure of time and the other one is a measure of length? And in this case, that is not possible. Okay? All right, number 2. You can always add two numbers that have the same units, like 6 meters plus 3 meters. Can you always add two numbers that have the same dimension, such as two numbers that have the dimension of length? Well, let's try to think of an example. Can I add 1 meter plus 5 inches? Not without converting. So it's not possible because we need to convert so they have the same units first. Ultimately, if they measure the same dimensional quantity, we can add them, but we have to make sure they have the units first, the same units first. Okay. Let's do a quick example of the unit analysis that we were just doing on the other page. So in this case, velocity is a length over a time. Let me make this bigger. Length over a time. And time is obviously a dimension of time. So when we cancel these out, they divide to 1 and we get a unit of length, which is the same as position. So this one works out just fine. And we verified that that equation at least yields the correct units. Let's try F. This is a unit of time, or dimension of time. And then here, we're going to have, the 2 is unitless, so we leave it out. We have a length, Acceleration is meters per second squared.